Hello, today we're going to be talking about quantum chromodynamics, a major part of quantum mechanics. Quantum chromodynamics deals with the study of the strong force and the charge associated with it, that is color. Now, color can exist in three types: red, green, and blue. Now, if you look at any nucleon, say a proton or a neutron, we can see that the two ups and the two down quarks seemingly violate the Pauli exclusion principle. So there must be something else that differentiates the two of them, and this again is nothing but color. Now, the gauge boson, or the force carrier of the strong nuclear force, is the gluon. Now, just as we've seen that the weak charge such as the W plus or the W minus boson can convert an up into a down or a down to an up, a gluon can change the color of a quark. Now the main difference between QCD and QED is that the gauge boson of the electromagnetic force, the photon, does not have any charge and does not interact with other photons. But as we shall see later, gluons do have a charge and indeed do interact with each other. Now gluons behave like a quark-anti-quark pair. These doesn't annihilate because the colors are different. Now let us see how you can convert a red quark into a green quark or a blue quark. Here we have a red quark coming in and going out, and we have a green bar pair production. Now what we can see here is the red quark becomes a green quark with the emission of a green bar red gluon. Similarly, we can also have a green bar green annihilation with a red quark coming in and going out, and this implies that a red green bar gluon is converted to a green quark. So this shows that the color can change by either emitting or absorbing gluons. Now you may have observed that the farther away you keep two magnets, the weaker the force between them. Now the force is given by the Coulomb force, which basically states that the force is inversely proportional to the distance. However, in a strong force, the force is irrespective of the distance. So basically what this means that it will take an infinite amount of energy to pull a quark or to get an isolated quark. Now in practice, even if we try to do so, the extra energy will manifest itself into a meson, which will further decay into an electron and a neutrino. And these jets or showers are what we study and analyze from particle accelerators. This is how gluons hold quarks together, and this is why it's extremely hard, basically impossible, to get an isolated quark. This is called quark confinement. Now let us talk about something called pion exchange. Now a pion is nothing but a meson with an up bar, a down a down up bar, or an up down. Now this may sound complicated, but it's just a meson, and just like how the gluons can hold the quarks in the nucleus or the nucleon, the gluons can also hold the nucleons in the nucleus. This is called the residual nuclear force, and by this method individual nucleons can be pulled out, since the force extends only across the width of the nucleus. The process by which nucleons are held in the nucleus is called pion exchange. So in simple terms, what happens is, as we have seen, gluons are emitted, which change the colors of the quarks inside, and over time this energy manifests itself into a pair production, which manifests itself into a meson, which is a pion. And if the proton emits it, it's absorbed by the neutron, and there's a similar process which is then absorbed by the proton again and into the neutron and the proton, and vice versa. Now this exchange is what creates the force that holds the nucleons together. So today we've learned about quark confinement, pion exchange, and quantum chromodynamics. If you have any doubts, leave them in the comments and any suggestions for the next video. And yeah, thanks for watching.